A motor car engine needs fuel, petrol, to keep it going. Inside the engine, the fuel is burned to produce energy. So there has to be an air supply because burning needs oxygen. It gets this through the air intakes and air filter. Without a continuous air supply, the engine couldn't keep running. We too get our energy by burning fuel inside our bodies, and we too need a constant air supply. Our lungs are the organs which provide us with the oxygen which we must have to stay alive. This simple model shows how they work. The glass jar represents our chest cavity. A glass tube divides into two branches representing the windpipe, and the balloons are our lungs. Closing the bottom end of the jar, there's a plastic membrane representing what we call our diaphragm. When the diaphragm's pressed upwards, compressing the air in the jar, the air is squeezed out of the balloons. When it drops again, air is sucked into the balloons. It's the movement of the diaphragm which causes air from outside to be sucked in and out of the balloons. This is partly how our lungs work, but our chest cavity isn't a fixed shape like the jar. It can be expanded and compressed by the movements of our rib cage as well as by the rising and falling of our diaphragm. When our diaphragm drops and our chest expands, air is drawn into the lungs. To breathe out, we push up the diaphragm and contract our chest. Let's take a look at the human lungs and diaphragm. She's having a routine chest X-ray. The small dose of X-radiation won't harm her, but the radiographer's working here every day, so she goes behind a protective screen, otherwise she'd receive a dangerous dose over a period of time.
Either way, that's fine.
You can't actually see the lungs properly, but there's the diaphragm. This is the heart. There's the bottom of the lungs. The spine goes up here. And you can see the rib cage and the collarbone. And here they are in action. There's the heart beating. And you can see the diaphragm moving up and down. Here it is at the other side. The diaphragm descends as we breathe in and rises as we breathe out. And watch the movement of the rib cage caused by muscles which we can't see in the X-ray picture. Now let's look at an actual lung, inflating and deflating as air is drawn in and out. There it is, the living human lung. Using a special instrument, we can look down the main air passages into the lungs. From the back of our throat, a single pipe, the trachea, passes downwards, dividing into what are called bronchi, side connections to the two lungs. You can see the glistening mucus, which keeps the passages moist and clears tiny solid particles out of the air passages. The passages divide and divide again, supplying air to different regions, different lobes in each of the lungs. And if this looks complicated, the lungs themselves are even more complex. This cast shows the intricate mass of air passages inside the two lungs. There are the main air passages supplying them. At the very ends of all the tiny air passages inside the lungs, there are little sacs called alveoli, and it's in the alveoli that oxygen from the air passes into the bloodstream, because the lungs also have a complex blood supply, bringing blood back to give out carbon dioxide and to collect fresh oxygen, which is carried away to every part of the body. This pale patch just appearing shows both blood vessels and air passages. The alveoli are too tiny to be seen clearly. In reality, the whole lung is a network of blood vessels and air passages. Using X-rays and a special dye injected into the bloodstream, we can watch this dye, carried by the blood, passing through some of the blood vessels in the lung. See the diaphragm at the bottom? Let's look at what happens inside the lungs. Here's one of the tiny capillary blood vessels in the wall of one of the alveoli. Oxygen from the air breathed in passes through and combines with a substance called hemoglobin in the red blood corpuscles. These corpuscles, now containing oxyhemoglobin, are carried away in the bloodstream through the network of blood vessels in the lung to the pulmonary vein, which passes into the heart. The heart pumps this freshly oxygenated blood through the arteries around the body, and the oxygen can be made use of wherever it's needed. Here are red corpuscles passing along a capillary blood vessel. Here's a capillary passing through some body tissue. The oxyhemoglobin in the red cells gives up its oxygen, which passes through to the living cells when it burns fuel, carbohydrates, in the cells, producing energy. Carbon dioxide is produced, and this dissolves in the blood and gets carried away. The capillaries are connected to veins which carry blood back to the heart, then along the pulmonary artery, back to the lungs. Back in the lungs at the alveoli, the carbon dioxide passes out of the bloodstream into the alveoli. It is then breathed out. Fresh oxygen is taken up by the hemoglobin in the red corpuscles, and they carry it away again to supply the living body, and so the process goes on. The more work our bodies have to do, the more energy they need, therefore more fuel and more oxygen to burn that fuel.
Start the clock, please.
Steve is just going to sit on the exercise bicycle for 5 minutes. Although he's doing nothing, he has to keep breathing, of course, because all the life processes in his body have to be kept going, and these use up some oxygen. Let's see how much air passes through his lungs in 5 minutes, what's called his ventilation. The bag holds 120 litres, and you can see that it's nothing like full yet.
Mouthpiece, please.
There it is after 5 minutes. The bag's not been filled. It would need much more time as long as Steve's not exerting himself. Now he's pedalling at a steady speed with a fixed loading on the bicycle, again for 5 minutes. After a short period, you can see that he's using much more air. The bag's filling quite rapidly. And after 5 minutes, he's filled the bag. 120 litres of air have passed through his lungs because his body needed much more oxygen to keep him going when he was working so hard.
You put the mouthpiece in between your teeth and your lips.
Another demonstration. Electrodes are attached to his body, and the gas he breathes out is connected to equipment which will analyse it chemically. There's his heart rate. That number is a measure of how much oxygen he's using up from the air he breathes in, around 3.7. His heart rate increases, and you can see that the number's going up, showing that he's using up more oxygen from the air he's breathing in. The more work we do, the harder our lungs and heart must work. We need more and more oxygen, and the heart must pump the blood carrying it faster and faster around the body.
Okay, going down, Steve. Okay then, Sally, take a deep breath.
We can measure how healthy our lungs are by seeing how quickly we can empty them of as much air as possible.
You ready?
Sally has to breathe out hard into the apparatus without taking a single breath in.
Good, keep going. Fine, great.
There's the graph she produced. We'll make it easier to see by tracing over it.
Blow as hard and as fast as you can.
Now Steve.
That's good. Keep it going. Keep it going. Well done.
There's his graph. Let's compare the two. We have time in seconds along the bottom and the volume of air breathed out in litres up the side. You can see that Sally breathed out nearly 3 litres and Steve, who has a bigger lung capacity, 4 litres. But they each have very healthy lungs because they could each expel nearly all that air in just over 1 second. For a healthy, active life, we must have healthy lungs and heart. We should all take plenty of exercise, not just because it's fun, but because this will give the lungs and heart hard work to do, so that they become and remain fit and healthy. Without clean, clear, healthy lungs, you can't lead a fully active life. Unfortunately, some people, while they're young, develop one habit which is the worst possible thing for both lungs and heart. They start to smoke. Here's a radiologist who knows only too well what can happen then.
Well, here we have a nice normal chest x-ray, clear, both lungs are shown to be fully aerated and there is no obvious abnormality. But if you come and look at this one, a patient who smoked regrettably 25 cigarettes a day for about 20 years, and here there is no doubt there is a very nasty tumour, and that is a lung cancer.
Many people, including an increasing number of women, die of lung cancer and other diseases associated with tobacco. The cancer can be removed and the patient will live a little longer, but there's nothing like a 100% cure rate. The surgeon is removing a diseased portion of the lung from a woman who's a heavy smoker. If you smoke, this could well happen to you. Here's the diseased lung and the cancer inside it, a cancer which can easily spread throughout the body and may in this case already have done so. Smoking is one of the great disease producers. It will almost certainly shorten your life. If you don't smoke already, don't ever start. If you do, well, there's a great possibility that one day you'll have cause to remember this film.